So I guess we're ready. I don't think I have anything more to say, except that this audience is great. They even knew what these things were, which I didn't. So, very perceptive. Have fun with the talk.
Okay. Hi, everyone. I'm glad that more than about 20 people are here. Room seems to be almost full. Okay, the title of my talk is Spoilers, Reverse Green, Decel. I don't know if any of you have ever been in the cockpit of an Airbus airliner during landing. Probably not many, but these are the announcements that the pilot not flying is making during landing. And let's see if I can find the video for that. This is an approach to Madeira Funchal. It is one of the most challenging approaches. So we can see everything. So there are some things that the airplane says, which is the height above ground. 400.
300. 200. 100. 40. 30. 20. Retard.
Now listen closely.
Retard. Retard. Retard.
And I'm sorry to disappoint you, this plane is not going to crash. At least not now. This is almost a picture-perfect landing in an A320. Things that he's saying now is 70 knots and taxi speed, which means reduce reverse thrust from maximum power and cancel reverse thrust. Those are the cues for those actions. So these are things that the pilot not flying can be either of the pilots. It can be the pilot in command or the captain, or it can be the first officer flying. And the other one is called the pilot not flying. And he calls out what he sees on these little computer screens. This is an old model which actually has 6 cathode ray tube displays and gives various indications. And the response to that is to announce that the spoilers, which are the speed brakes, have come out of the wings, and that the reverses, the thrust reversers are fully deployed, which is indicated in green, and that the aircraft is achieving the intended deceleration, which is indicated by another light, and that's the announcement for that is decel. That's actually what it says on the lamp, but you can't read it in this resolution video, I think. So now we have the first crash, actually. This is one that, all right, this is the one. Some of you may know it, some may be too young to remember it. This was one of the very first Airbus A320 with full fly-by-wire. Did a flyby at a small rural airport at Mulhouse, Harpsheim. And did a very spectacular, very low, very slow flyby, and oops. Oh la la. Yeah. The pilot did various mistakes in preparing the flight and in performing the flight. He was too slow, and he was much lower than intended. He had deliberately deactivated a safety system that might have gotten him out of this situation early enough. Then again, perhaps not, because he was too low for that safety system, which gives maximum thrust to activate anyway. So this is probably caused by over-reliance on the automation. He thought, oh, the airplane is doing fine, and I can do it. And this is the new toy of Air France. It was in 1989, just a few months after introduction into line service of this brand new aircraft, the first airline of the world with completely digital fly-by-wire control. Okay, let's get back to the talk, which I'm afraid is a little less spectacular, but might be interesting anyway. So that was it. What's it doing now is the prototypical question that is asked by pilots when the autopilot system is doing something unexpected. So the computer is flying the aircraft, which is called the autopilot, and it is doing something other than the crew was expecting. So what's it doing now? This is not unique to Airbus. This happens to all modern airliners which have an autopilot, which is all of them. We have a little company, we do consulting work, causal accident analysis of airline accidents, and we recently bought this aircraft. It's just a little one. It was a bit cheaper than a big airliner. It has only one engine. It has 2 fuel tanks. And these are, I think these two, the stick is in the way, but these two are the fuel gauges. And somewhere here is fuel pressure, I think that one. So it has 2 tanks, 1 pump, 1 engine, 3 gauges, and that's about it. We haven't got the airplane yet because the weather was too bad for the ferry flight, but we will soon. Okay, just for comparison, there's the Boeing 777, which is so far one of the safest airliners to fly, which has more, it is the only one which has more than 2 million flight hours and not a single fatality, which is rather impressive. But the point I'm making here is it has 3 tanks and 2 engines. It's not that much more. I mean, there's combinatorial complexity, so it's a little more. How complicated can it be? This is the actual display. In fact, it is green on black, but this is from a manual, and that's black on white. This is the so-called fuel synoptic display. This is what the pilots see about the state of the fuel system. We have left wing tank, which is called the left main tank, the right main tank, and the center tank. 2 crossfeed valves. If one tank doesn't work for any reason, then both engines can be fed from one main tank. These are the pumps, 2 pumps in the main tank and 2 pumps in each wing tank. It's not that complicated, is it? Well, actually it is. This is the complete fuel flow diagram, and this is excluding the engines. So this is just the rhomboids, and at the top are the engines. The left one is the auxiliary power unit, which also needs fuel. Somewhere here are the tanks, center tank, left main tank, somewhere here is the right main tank, and fuel flows back and forth, because what really happens is the center tank is emptied first, and then when a certain level is reached, then the boost pumps from the center tanks switch off, and fuel is used from the wing tanks, and small scavenge pumps, which are driven by the main boost pumps, which are jet pumps, pump the rest of the fuel from the center tank into the wing tanks, and all sorts of nice engineering stuff going on. It's a rather good system. It has worked very reliable so far. There doesn't seem to be a problem with it. But it's much more complicated than you think at first. The engines themselves have a diagram of about that complexity, fuel flow inside the engine, but I don't show that here. The problem is how much of this to show to the pilots. You obviously wouldn't want them to show all of this with everything green if all is fine and some parts in yellow when something is not fine. So there's the task, what to show to the pilots. If you show them too many lights, all they see is basically a Christmas tree. And if you do too many warning sounds at the same time, the human brain can't distinguish. Maybe the guy who's talking tomorrow can tell me more about exactly how many. It's on the order of 6 to 7 or 8 or something like that, different sounds. And if it's any more than that, you don't hear anything. You just cacophony. On the other hand, if you present too little information, you may be making suboptimal decisions because you don't know all of the facts. And this is actually a big part of fully computerized display systems on aircraft, is prioritization of error and warning messages, so that at one time they usually only get one, It's displayed in the lower part of what is called the ECAM in most aircraft, the Electronic Centralized Aircraft Monitor. And if another event happens of higher priority, it replaces the current message. And then you have to read the message, read what you have to do it, and then press OK, sort of like a dialog box on a modern GUI. Except that most of these interfaces predate the modern cursor and mouse interfaces, Windows and mouse interfaces. Well, here we have an accident, one luckily without any fatalities. It was a Boeing 777. It is so far the only hull loss. That is the only total loss of a Boeing 777. During final approach, the engines produced a lot less thrust than was actually required. Slightly above idle, but not as much as needed to keep them at a constant speed on the glide path towards the runway. The crew did an extraordinary job getting it to the airport. When they first noticed something was wrong, they thought they were ending up on the tube station and killing hundreds of people. And when they changed the configuration of the aircraft so it would glide a little better, he said, oh, great, now we're only going to kill 250 people instead of 500. Great. And in the end, they made it over the perimeter fence, maybe 1 or 2 meters to spare. Whereas I wrote landed in the grass. Actually, they crashed pretty heavy on the grass, and the landing gear punched through the wing. They skidded through the grass and ended up at the runway threshold. The aircraft was damaged beyond repair. One guy, I think, broke his leg because the landing gear impacted the fuselage, and fuselage skin is rather soft, so it punched through and broke his leg. They landed with about 10 tons of fuel, but luckily there was no fire. And we sometimes think about what would happen if they had actually made it to the runway and made this crash landing on the runway instead of on the grass. There would have been quite a lot of sparks, and there might have been a fire, and it might have ended a lot worse. As it was, only one major injury, no fire, no fatalities. And I have a little video for this one too. This is, I'll close this one. This is the screen, sort of like that the tower air traffic controller gets. And, it's coming in about here in a couple of moments. There it is. That's the accident flight.
Hello, continue approach 27 left, the wind is southwesterly at 10 knots. Continue, Shotton Whiskey.
So nothing happens for a while. He already knows he's in trouble, but he's busy reconfiguring the aircraft and doesn't have time to tell anything about it, to tell anybody about it.
Mayday, mayday, Speedbird, 95, 95.
Mayday, mayday. Speedbird is the call sign for British Airways aircraft. This is several aircraft trying to transmit at the same time.
Aircraft accident, aircraft accident. The position is the threshold, runway 27 left. Aircraft type is a 777. Natural problem is crash. Aircraft has crashed.
The interesting part is more or less over now. Then you can see the quick emergency service response. What he said, well, there was an accident, aircraft has crashed. It is a 777, the aircraft has crashed. And it is interesting to see how quick emergency service response is on that one. But that's more or less what the air traffic controllers see and hear. They see the plane approaching. They may notice, if they're very observant at the moment, that it's getting slightly slower than usual. But the first real indication that there's a problem is the mayday call in this case. Mayday, mayday. And then they call the emergency services. So what happened was there probably was fuel pipe icing, and the engine just didn't get enough fuel. Obviously, all the evidence melted rather quickly because it was in the engine, and nobody knows for certain. The British Aircraft Investigation Branch said it was fuel pipe icing. They say it in a rather definitive tone, but we are not so convinced because they could reproduce some kind of fuel pipe icing, but only with a much higher water content in the fuel than was actually measured in the fuel with which they landed. There were big discussion about the fuel. It was Chinese fuel, and said, oh, Chinese fuel is substandard and blah, 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 and everything. But the fact is that thousands of flights every day fly with Chinese fuel, and they all fly fine, so I don't think there's really any problem with it. Yeah, the FADEC, which is the Full Authority Digital Engine Control, it means the pilot just gives a demand, how much thrust he wants, and the computer inside the engine controls the engine parameters, which is basically fuel flow and some variable state of vanes that guide the airflow in the compressor section. There's not a lot more to control, actually, but it ensures that the engine won't stall during acceleration and will accelerate usually as fast as it can. The FADEC commanded the metering valve completely open. There's a control loop in the control software which is called absolute maximum fuel flow, which is the fully open position of the valve, which is never used in normal operation, not even during takeoff, where the maximum thrust is required. But that was the control loop in which it was. Had written that to the non-volatile memory of the FADEC. So we know what happened. But still, not enough fuel was arriving in the combustion chamber. But the FADEC already noticed this discrepancy. It noticed, well, the thrust levers or the auto throttle are demanding a lot of thrust. I cannot give this thrust. I've opened the valves fully and there's nothing, but there was no cockpit indication of this discrepancy. You might think that might be important enough to display it in the cockpit in some way. And they really only noticed it when the nose of the aircraft began rising to keep the glide path. And it was almost too late. And they did the right thing. They retracted the flaps, the high lift devices a little bit and made it to the airport. But this is an example of the important decision when designing the software for display in the aircraft, what to show to the pilot and what to withhold so as not to overload the pilot with information. There's no clear-cut answer to that. It is a decision that has to be done together with pilots, with air traffic controllers, with the engineers, and they all have to sit together for a long time and decide what to show under what circumstances. And then the regulatory authorities, the FAA in the USA and the EASA in Europe, have to say they're happy with that and will certify the aircraft. So there's another one. This, unfortunately, was not quite as happy in the ending. Almost everyone on board died. So what happened? It's an older type of aircraft, an MD-80, derived from the McDonnell Douglas DC-9. They have a sensor which measures the so-called RAM air temperature. It is the total temperature, that is the temperature of the surrounding air, uncorrected for the oncoming speed of the air. So it measures static air temperature plus the movement of the molecules relative to the aircraft because of the airspeed, and gives a higher temperature reading. But actually that is the only temperature that can be measured directly. And on these Boeing aircraft, it's called a RAT sensor, the RAM air temperature. They noticed a RAM air temperature of above 100 degrees Celsius on the ground, when in fact it was only about 30 degrees in Madrid. And so they returned to the gate, retracted the flaps. They were already at the runway threshold and noticed something is wrong, so we returned. A technician noticed, well, that's not a problem. We don't expect any icing conditions, so we can just pull the circuit breaker that heats the probe to keep it from icing up when you fly through icing conditions. And then for every aircraft, there's a MEL, a minimum equipment list. It is a list that also has to be acknowledged by the regulators. The minimum equipment list specifies which equipment must be present and functioning properly in order for the aircraft to be allowed to perform a line flight, to be dispatched, as the term for that is. And the minimum equipment list says you may fly without red probe heating if no icing conditions are expected on the way. So the technician and the pilot in command, the captain, decided then it was okay to just pull the circuit breaker and fly. And they made a second takeoff attempt. They didn't extend the flaps. In particular, they also didn't extend the slats, which are coupled with the flaps. And the slats are the leading edge devices here, which increase the stall speed, the stall angle, which is the angle at which the boundary layer separates from the airflow over the wing, and the wing rapidly loses lift. And the slats prevent that by about 5 to 8 degrees, increase the stalling angle. So they took off without flaps, lifted off, climbed a little bit in ground effect, very close to the ground. The lift is a little bit higher than when you clear off the surface. It descends again and crashes by the side of the runway. So what happened here? This is actually just a small portion of a large piece from the maintenance manual from the MD-80 aircraft. There are a couple of systems that have to work differently, whether the aircraft is on the ground or in the air. And there's a switch in the nose landing gear, which has a air mode, ground mode switch. And the switch switches the voltage, which supplies a couple of relays. One of these relays is particularly important in this incident, or rather in this accident, it is called R25. I don't know if you can read it from the rear. This one says air data sensor heating. So air data sensor heating, the air data sensors, of which the ram air temperature sensor is one, must be heated in flight, but they must not be heated on the ground to avoid wrong readings. But normally they are always heated in the air, so you cannot forget to turn them on when you encounter icing. The current that they draw is not significant given the engine power that you have available on a modern jet. The other one is takeoff warning. There's a takeoff warning system which blows a horn, quite literally, when your takeoff configuration is wrong and you apply full takeoff power. It's called the TAWS, the takeoff warning system. Sometimes there are different acronyms for these, depending on the manufacturer. The takeoff warning system obviously should be inhibited once the aircraft is in the air, because in the air you fly with the flaps and the other high lift device is retracted, and it shouldn't warn you when you do that. But the technician didn't look into that, just pulled the circuit breaker for the wrapped probe heater and decided the aircraft was fit to fly. And indeed, the pilot noticed that the ram air temperature indication now read 30 degrees and decided everything was fine. What they didn't know was that this relay was probably stuck in air mode, so it heated the air data sensors, and it also inhibited the takeoff warning system. So the takeoff warning system was off, and they took off with the wrong configuration, but the takeoff warning system didn't warn them. So, with the known consequences. This is the accident analysis method that we use at our working group at the university. It's called Why Because analysis. Some of you may have looked at the Why Because homepage, which was linked from my entry in the conference system here in the web pages. And in this overview, you probably cannot read anything. I think this is actually the graph that a group of students made in the lecture in this semester when we talked about this accident. It has various parts. This is simplified so that you can read the more important pieces. But I think most of you will already have some kind of understanding what went wrong. This relay is stuck in air mode, so the air data sensing heating is on, which is noticed by the crew. The arrow in this kind of graph means is a necessary causal factor of, and we use the counterfactual test to decide which is a necessary causal factor, which means if there's an arrow between them, it means if this had not happened, then this would not have happened either. So that is the criterion that we use to determine causality in the way that we use these graphs. So crew returns to the stand. The flight is already delayed because the crew returns. Taxiing back and forth takes about 15 to 20 minutes. And this is here the red reading returns to normal. So what we can see about that. Right. The takeoff warning system is not powered, which is also because this relay is stuck in air mode. They examined the relay after the accident and found that they couldn't reproduce the malfunction. But if you know about Occam's razor, which is if you have several explanations for something, then usually you go with the simplest one, which explains everything in a satisfactory fashion. So going by that, we deduced that probably this relay was stuck in air mode, because otherwise you would have to have an enormous amount of very unlikely things to happen and erase the traces after the accident. So we assume that this was what actually happened. The relay was physically damaged, so we cannot say exactly with absolute certainty if this was the case, but it seems to be the most probable explanation. So when returning back to the stand, you retract the flaps. This is standard procedure. The flight is delayed, and the pilot in command and the technician decide that the aircraft is fit to fly on a revenue flight. The flight is delayed, so the crew may have been under pressure. We used this double frame around the notes to denote that this is an assumption. The crew died in the accident, so we cannot ask, and we don't know what actually was on their mind. But it seems a rather reasonable assumption that the crew was under pressure and hurries through the checklists. Normally you have to read the checklist item by item and confirm, actually by looking there, that the actions have been performed, or if not, perform them. And that includes for takeoff, obviously, to extend the flaps. So, and this is the last one. The crew think they are properly configured for the given takeoff speeds and runway lengths and everything. They rotate too early, that is, they raise the nose of the aircraft at a too low airspeed and try to lift off. And because they don't have any high lift devices available and they're flying too slow because the flaps and slats remain retracted, there's insufficient lift, while the aircraft descends again once out of ground effect, becomes uncontrollable, touches the ground with the wingtip and engine and the tail cone, and crashes. Only very few people survived this accident. Most of them were thrown from the aircraft into a nearby river where they could escape the fire. But many died on impact and many others asphyxiated or burned. So if you look at it now, in many cases you would say, well, yeah, of course they should have extended the flaps. And of course they should have looked into why the red probe heating was actually on in the first place and not just say, oh, it's on, we just pull the circuit breaker, so it's off now, we don't need it, okay, we fly, right? One of the safety devices that many modern airliners have, because the behavior once the airplane has stalled becomes uncontrollable. So they have a warning device, which is called a stick shaker. Once you approach the angle of attack, the angle at which the air meets the aircraft, exceeds a certain value, the stick, the control column on most modern aircraft, they have a yoke, really, on the top of a stick, shakes violently, which alerts you to the fact that you are about to lose control if you continue pulling the nose up. And you should always respect the stick shaker. There's also a horn, and in most aircraft, pardon, what's so funny about that? Yeah, that's just what it's called, right? You should respect the stall warning. In most modern airlines, there's a synthetic voice which shouts at you, stall, stall. And you know that you better push the stick forward and lower the nose, gain some speed to get out of the stall. Recently, just a month or two ago, there was an accident with an American C-17 military transporter, a big one, 4 engines. And one of the instructor pilots, actually, one of the instructors, decided that the stick shaker in the C-17 was unreliable and should best be ignored. And I don't have the video for that now, but it's on YouTube. You can look for C-17 crash or something, you'll find it. It stops immediately before the crash. I think it was an official video released by the military. And he tried to perform a spectacular maneuver for an air show. It was a rehearsal for an air show. Pulled it into a very steep curve at about 90 degrees bank angle, pulled too hard, stalled the wing, and, well, just flew straight into the ground. As a colleague, accident investigator, once said, he made it straight to the crash site. There's a saying about privately owned small two-engine aircraft, and the second engine is there to get you to the crash site. Because most take off too slow in them, and if one engine fails, within just 1 or 2 seconds it'll just flip over. And if it happens just after takeoff, it'll drive you straight into the ground. So the other thing is, of course, if there's a malfunction, look for the reasons of that malfunction and just say, oh, we cure that malfunction by curing the symptoms. And of course, be sure to understand what the minimum equipment list says and what it actually means. It means if the red probe, in this case, it means if the red probe heating is defective and doesn't work, although it is turned on for some reason, then you may fly without it, if no icing is expected. It doesn't mean if it's activated on the ground for an unknown reason, you can just deactivate it by pulling the circuit breaker. So we don't know how far spread this misunderstanding of minimum equipment lists actually is. So we can't say much about that, but it is really what you should do. So the next one. First we had one crash, no fatalities. Then we had one crash and several fatalities. But some survivors, now we have 2 airplanes crashing in one accident and everyone on board dying. So luckily, if you can say such a thing, and the B757 was a cargo aircraft and only 2 people were on board. On the other hand, the Tupolev had a lot of families and children on board. So they were on intersecting trajectories above Lake Constance, or converging in the vicinity of Lake Constance. Both were equipped, because they must in most countries, with the modern onboard collision avoidance system called ACAS or TCAS, depending on whether you live in Europe or in the United States. TCAS is also the name of the implementation, the only available implementation actually, by Honeywell as far as I know. There was only one air traffic controller actually working the area. He noticed the situation rather late. What constitutes rather late in this case is about 50 seconds before the projected impact. This may seem rather short, but it is by far enough time. About 20 seconds would be enough. In that case, the air traffic controller orders one of the aircraft and says, descent flight level 350, expedite. And when he says expedite, it means right now and quickly. Usually also gives a reason, and in this case, he realized that they were on a course in which they might collide. The chances of actually colliding are very low, because they fly fast and they only take up a little volume in space. He realized the situation late, and because he had to also manage approach to Friedrichshafen Airport. And he gave a reason to the Tupolev to descend to flight level 350, that is 35,000 feet. He said there was conflicting traffic, but he told them it was on the other side than it actually was. He told them it was to the right side when it was actually on the left side. So the situation they were faced with was, we can see one here, and air traffic control told us there's another one there, which we can't see, because they have no reason not to believe the air traffic controller when he tells them there's traffic at, at 2 o'clock. At almost exactly the same time, almost to the second, as the ATC, the air traffic control, instructed the Tupolev to descend by 1,000 feet, the onboard system called TCAS instructed the aircraft to climb. And TCAS always gives divergent instructions to two aircraft on a collision course. So if it tells one to descend, it tells the other one to climb. And the hope that at least one of them follows the instructions and none of them maneuvers contrary to the instructions. What actually happened was that both airplanes descended, and as luck would have it, they collided. And both were completely destroyed, and all people inside the aircraft died. As far as I know, nobody on the ground died. The pieces fell into a forest, some probably fell into the lake. This is the TCAS kit, this is the hardware. The details aren't very important in this case, but if you're really interested, you can ask me afterwards. This is the antenna that is normally used for the transponder. That is, if an airplane receives a radar signal, it responds with its altitude and identification with this antenna. This is the antenna that also receives Mode S transmissions from the other aircraft. So the aircraft see each other. This antenna is directional, not very much. It has a directional resolution of about 15 degrees, but it has a rough idea, thank you, has a rough idea from where the other aircraft is coming and how fast it is approaching. And it also knows, because it is transmitted, digitally encoded, it knows at what altitude the other aircraft is flying. Of course, it knows at what altitude it is flying itself, and there's some complicated and mostly secret algorithms inside the TCAS2 unit. And via Mode S, two airplanes can exchange messages, and they negotiate which one of the aircraft is going to descend and which one is going to climb. And if a certain closure rate is met, the threshold is met, then it issues what is called a resolution advisory, which says it tells one aircraft to climb and it tells the other aircraft to descend. It actually only has a synthetic voice and an indication on the instruments. It does not actually maneuver the aircraft, it just tells the crew what to do. So it is called, not a command, it's called a resolution advisory. Here's how it works. This is the threshold. If it's 45 seconds to the projected impact, it issues what is called a traffic advisory. It just says traffic, traffic, and there's a little display in which it paints the other aircraft on a collision course in yellow. And if the threshold to impact is 30 seconds, then it issues a resolution advisory. And if the closure rate is very low, there's another protective area around the aircraft, and if an aircraft enters this protective area, then there are two thresholds, one for the traffic advisory, which just tells the crew that there is some other traffic on a potential collision course, and if it enters the red circle, it also issues a resolution advisory. That is, it says climb, climb, or it says descend, descend. And this is the state that we have here. This is the internal cognitive state as we inferred from what we know about the accident. This is the DHL, this is the Boeing 757. It knows there is a conflict, and we descend. And since they got a descent advisory from the TCAS, they assume that the conflict traffic is climbing. They also know they have a TCAS conflict, but because the air traffic controller gave them wrong information about the direction of the conflict, they think they have another conflict, which is not on the TCAS, and which they cannot see. So they may assume that it is a military aircraft. They are not required to use their transponders. They communicate on other frequencies. They may fly under certain circumstances without position lights. They have all sorts of exemptions from civil air traffic regulations to perform their duties. So they think there's another aircraft. They think they're in a three aircraft conflict, which in fact they are not. So they decide, we try to avoid the aircraft that we can see and follow air traffic control to avoid the aircraft that we cannot see. because they assume air traffic control sees the other conflict, knows where it is, and takes us away from it. They know, the air traffic controller knows, because you can see that on the radar screen, that the Boeing is at flight level 360, and they assume, because they've instructed them so, that the Bashkirian Airlines, the Tupolev, is descending from flight level 360, 1,000 feet. So they have no new information. The aircraft have no new information, but the controller now knows that the Boeing is also descending because it has received a TCAS resolution advisory. And very shortly afterwards, the two aircraft collided in the air, and the controller has a blank screen. Now here's an interesting problem for the designers of such a system. What is the system? Is it only the hardware and the software? We find that in many cases it makes a lot more sense to also include the crew in the system description. We will see why a little later. Or we have the kit plus 2 crews of 2 aircraft. And it makes a lot of sense to also include air traffic control when we look at the system and look at system behaviors and look at what it is doing and what it should do and what it cannot do. So we have come up with a couple of principles for interactive systems to avoid these kinds of situations. We need to have what we call rational cognitive model coherence. That is, all participants in a task must have a coherent state of the world in their image of the world, so to speak. So if they know about certain parameters like altitude of other aircraft and maneuvers of other aircraft, all of them must have the same idea of these parameters. It may seem trivial, but in this case, that was not the case. The system was not designed to ensure that, because the TCAS designers considered the hardware, considered the hardware and the software to be the system and didn't consider the influence of the other participants. There's no procedure where TCAS resolution advisories are immediately communicated to air traffic control. And there's a saying in aviation about the priority of actions that you take, which is aviate, navigate, communicate, in this order, always. So first you make sure that the aircraft flies safely. It doesn't stall, it doesn't overspeed, it doesn't fly into the terrain or whatever. A second is navigate. You make sure you know where you're going and where you are. And if you're sure about the aircraft is flying safely, you know where you are and you know where you're going. And then you tell air traffic control. And in the case of a TCAS maneuver, that takes some time. It may take about 20 to 30 seconds to have done the aviate and navigate part and actually tell air traffic control. And during that time, air traffic control has no idea that you got a TCAS resolution advisory. So this is violated. Another thing is, which doesn't play a big role in this one, but played a role in the British Airways Flight 38, the one that landed 400 meters short of the runway in my first example, is bounded rationality. You must see to it that you never put a rational task, to the agents in this task that is beyond their capabilities. Didn't play a big role in this one. The other one is that all agents, the mutual cognizance of relevant parameters, all agents must know which are the relevant parameters. It is not enough that the parameters about which they know are coherent between agents, but all relevant parameters must be known by all of them. And in this case, again, it was violated by the design of the TCAS system. It didn't provide any provisions, and it also didn't think about that ATC might want to know immediately about TCAS resolution advisories. So it just didn't enter the equation there. And procedural completeness, for every reachable state of the global system, which is in this case TCAS kit on both aircraft, 2 crews, air traffic controllers, for everyone there must be an explicit procedure for every reachable state. And this also is not the case in this one. And I'm not saying it's easy or trivial, but it should be a guiding principle when designing such systems. In this case, again, there was no procedure for the Tupolev aircraft. They got conflicting instructions. ATC said descend, and the TCAS said climb, almost within the same second. So what can you do about that? Right, the TCAS specification, the TCAS technical system, the kit, the hardware and software in this case, performed to specification. But there's one case where the TCAS system can issue modified resolution advisories. They may issue an increased climb, which is called increased climb. It just says increased climb, which means you should climb with 2,500 feet per minute instead of 1,500 feet per minute. Well, I'm afraid commercial aviation is still all imperial units, so they fly in knots, and they fly at altitudes in feet, and fly miles, and things like that. And there's also a reversal resolution advisory, which instructs an aircraft crew that had previously been instructed to climb to descend now, and vice versa. The voice phrase that is used for that is at first climb, and then descend now. So you hear that there's a big change now, and then we shall climb afterwards. This was a perfect example where a reversal RA should have been issued and would have resolved the conflict. But it was known that this was not in the algorithms, and it had also been discovered that this might be a problem. There was a change proposal, but changes in the TCAS system, as it is mandated for the airlines, take a very long time. As far as we know now, they take about 10, 11, 12 years to get implemented. So yes, the TCAS system performed to specifications, but the specifications were flawed. And what is also very interesting is the official accident investigation report by the, I think it's called Bundesstelle für Flugunfalluntersuchung, something, bfu-web.de, something. They said, well, the TCAS system performed to specification. Everything was working perfectly with the TCAS system. Yeah, well, sort of. But it is still, if you apply the counterfactual test, the TCAS system was a causal factor to this accident. So the very accident that it was designed to prevent was actually caused in part by this system. If we look at it, if there had been no TCAS system in both aircraft, then the Tupolev would have descended according to air traffic controller instructions and would have continued flying at flight level 350. The Boeing would have continued flying at flight level 360. Nothing would have happened. We never would have heard about it. The reverse is also true. If air traffic control had continued being unattentive, had slept or hadn't been there at all, whatever, then TCAS would have resolved the conflict. So actually both are causal factors in this accident. Take one away, either air traffic control or TCAS, the accident wouldn't have happened. So what could be the conclusions? Yeah, well, I wish there was an easy solution. Automation can be problematic. It can lead to complacency. The computer can now fly modern airliners, almost all of them, to many airports, not to all of the airports, but to many airports, from 100 feet above the ground when the autopilot is engaged, up to the point where it leaves the runway after landing. It can perform fully automatic landings. And as we have seen in the first examples, the amount and the way of presentation to the crew is also a non-trivial design challenge, and a lot a lot of effort goes into these things, as well as the mechanical engineering and aerodynamic engineering. On the other hand, when all goes well, automation drastically reduces workload of the flight crew. As I said, it does most of the things automatically. And since the vertical separation in most airspaces, or in many of them, has been reduced from 2,000 feet to 1,000 feet, commercial airliners now must be flown on autopilot in cruise. So it is not allowed to hand fly them, because you cannot fly precise enough. Well, it also makes maneuvers possible that are impossible without it, and here's the last video. So, what can you see? It is a fully automatic Category 3 landing. And no sane pilot would want to try that without the computers. It's altitude and feed. So almost up to the point of touchdown, you can't see a damn thing. But the computer has a very precise radio guiding beam and radio altimeter, so it knows what it's doing and performs a perfect landing. Automatic landings are usually a little harder than very smooth manual landings, but not necessarily uncomfortably so. So, where are we? Okay. I think 2 more points. Most of you will heard about Qantas Flight 32. I think it was 32, wasn't it? They had what is called an uncontained engine failure. And what is also the parlance used in the official report is that the turbine disk was liberated. So the turbine is, the high pressure turbine is spinning at, I don't know exactly, above 10,000 revolutions per minute. And the turbine disk is, high pressure turbine disk is about this in size. It's a solid disk of a very heat resistant alloy. And it just fractured into three pieces. I think 2 of them are lying in the Indonesian rainforest now, and they will probably never be found. And it pierced the wing, pierced several other parts of the structure, severed a fuel pipe in the wing, and severed many electrical wires in such a way that control of the other engine on that side was also lost. The wing was structurally weakened, not dangerously so for normal flying, but still, it'll be out of service for a couple of months. And these are, I don't know how well you can see them or if you can read them, but it's not really important. These are the kind of messages that you get on the electronic centralized aircraft monitor, the ECAM. And they got so many of them because so many systems were damaged that they were occupied. 5 people in the cockpit, 5 fully qualified pilots were in the cockpit, with just acknowledging these kinds of messages about what systems were damaged, what other systems were unavailable because of that, or what other systems were degraded to what degree. And by a factor of how much the landing distance has increased because not all the spoilers are available and stuff like that. But in the end, after going through that, there was no immediate danger to the aircraft. It can fly fine on 2 engines and can fly almost without restrictions on 3 engines. So they had time to do that. The crew had a very good idea of what actually was wrong with all pieces of the aircraft. They knew how much landing distance they were going to need, which was just short of 4 kilometers. And not many airports have runways that long. But there was one, the one they took off from actually. It was just a few minutes after takeoff, so they returned. Flew a couple of circles to burn some fuel and to just acknowledge all the error messages that they were getting. But they probably would have done that too if there was no immediate danger, just to dump fuel. And they had taken off for a long-haul flight, so they had a lot of fuel on board, and you don't want to land very heavy, so you just dump the fuel. But it takes time. They took about, to dump fuel down to the maximum landing weight, the maximum normal landing weight, would have taken far more than an hour. So they could do both of that, just look at all the messages and know everything that has failed or was degraded. And they could make an informed decision for landing, and they made a, under the circumstances, perfect landing, and stopped just at the end of the runway. The reason for that was not that they couldn't have stopped earlier, so it wasn't a very close call actually, but they decided to brake as smoothly as possible because they didn't have reverse thrust and didn't have all of the spoilers available, so the aerodynamic drag was much less than usual, so they didn't want to overheat the brakes. But this is what the electronic information system is pretty good for, and it did a good job. And the aircraft held together quite remarkably, given the damage that it suffered. And Rolls-Royce is going to have to do some homework in getting the engine fixed. They know what the problem is now, and hopefully they're going to fix it, and hopefully no other problems like that will crop up in the future. All right, one more thing, there's an NTSB study. The NTSB is the National Transportation Safety Board of the United States. It is the independent body that investigates transportation accidents, road traffic, rail traffic, and ships and airplanes. And they made a study about general aviation aircraft, privately owned aircraft, and found that those with a glass cockpit, with computer screens, had fewer accidents, but had more fatal accidents. And the reasons for that are still not quite clear. So that's what it looks like. This is a Cessna, I think, and this is a traditional steam gauge cockpit with electric and vacuum-driven mechanical instruments. And they're almost exactly the same on almost all aircraft. So if you've flown one, you can fly others. And these are, well, they're sort of like Windows and Mac, so they're quite different. They're all closed source, yes. So that may be one of the reasons that they are so different, and people are not used to that and do stupid things with it. So, right, as we said, automation can help enormously, but it is absolutely no substitute for a well-trained crew. You need the well-trained crew for the cases in which the automation fails. That's why they are well paid. Oh, well, most of them are. Some regional airline pilots actually are not, but that is another matter. Proper use of the correct level of automation must be trained. That is, landing in the visibility conditions that we have seen, everybody should use the automation, this is obvious. In cruise you must, but in fair weather, approaches can be hand-flown to maintain proficiency. Some airlines are actually now encouraging that again. Sometimes a lot of airlines said the highest level of automation must always be used because the computer can fly the airplane better than you. But they're coming back from that a little bit, at least some of them, and realize the value of properly trained pilots. Okay, that was it. Thank you very much.
Thank you, Bernd. So, questions?
Thanks for a great talk. You've emphasized that good training is important. When you have these low-budget airlines, like there's Lufthansa and Germanwings, they tend to have very young crews. Would that worry you?
Yes, not especially that they are young. One of the things is, of course, that there should always be one experienced pilot on board. And in fact, this is the thing that we have seen in recent years. For decades, almost since the beginning of commercial flight, safety has increased dramatically every decade. And this is the first decade in which this is no longer true. So we're not yet seeing a decline in safety, but we don't see a big improvement either. And we have actually seen some accidents where pilots did absolutely stupid things. And normally the NTSB in their reports is very moderate in tone and says, yeah, maybe the pilot could have done this. And there was recently one accident where the NTSB said, talked about inappropriate reactions of the pilot and inappropriate qualification of the pilot. And I've never read that before in an official investigation report. So yes, that is worrying.
Yeah, you've talked about the mid-air crash in Überlingen.
Where are you? Sorry. Oh, okay.
You've talked about the mid-air crash in Überlingen, and I've learned the system works that if there's two planes, it tells the one to climb and the other to descend.
Yes.
What is the plan about 3 planes?
Nobody knows, actually. It has only been verified for 2 airplanes. We don't know what it does with multiple aircraft conflicts. The manufacturer says, well, it just splits them into 2 aircraft conflicts and handles them separately. We're sure that it doesn't work for N above 4 or 5. We don't know exactly if it always works for 3. It might.
Short interruption. If you leave the room, please leave on the front, but please stay for the questions anyways. Thanks.
Mike?
Okay, I have a question from the internet, and the question is, when you analyze the cause of these airplane crashes, how do you deal with the knowledge that lots of people died in those crashes? How do you cope with that?
Mostly we just try not to think about it. We just look at it as objectively as we can.
Okay.
Yeah. We're not personally involved usually with any of these. What we usually do is after a crash and sometimes after the official investigation, we are asked sometimes by involved parties to do an independent analysis of that.
Thank you.
I have a question. Basically, you said it sometimes takes around 10 or 11 years or something like that until problems that are seen in the systems in aircraft are properly addressed, basically.
Yeah, normally not problems in aircraft as such. The only thing was that it has taken for this reversal RA to be mandated in all TCAS systems has taken that long, but usually it goes within months.
Okay, so that was an exception, because otherwise that would be really, really bad.
Right, and the TCAS system is not, strictly speaking, directly part of the aircraft control systems. It is more or less a separate system. It has no control over the aircraft. It is just an announcement system.
Yeah, certainly, but if something might kill people, then I think it shouldn't be taking 10 years.
Certification criteria are strict on these things too, which is part of the reason why it takes so long.
So are there differences between different countries, how countries handle these kinds of defects?
No, what exactly do you mean?
Well, you know, is there a difference between, say, a cheap airline in India or whatever?
You mean the airlines? No, the airlines are always subject to the regulations. If the regulator says your airplane may not fly that type of aircraft, then you don't. Right? Until they're satisfied that you're doing the right thing. No. Usually, the 2 main certification agencies are the FAA in the USA and the EASA in Europe and the EU. And most of the time, it is quid pro quo. Well, they all have to be satisfied that the airplane is safe enough to fly in line operation, which is very strict. But it is so that the FAA certifies Airbus aircraft and EASA certifies Boeing aircraft. Well, normally they have the airworthiness directives, which are regulations about things that have to be done to an aircraft so that it may continue to be allowed to keep flying, are almost always word for word identical between the American and the European regulative authorities. They really work together on that, and almost they usually release them on the same day with the same wording, just small differences. So most of the other countries who have their own regulatory authorities follow the two big ones generally.
Why do air traffic controllers and pilots communicate by saying left and right and not north, south, east, west? Because when you're at sea and you have lots of ships leaving a port, and that's a real mess, you use these directions. You say east, west, north, south, and you don't say left, right. Because left, right, you get mixed up.
What you do is you normally give a heading in degrees with 1 degree resolution. You say turn left, heading 170, something like that. The indication that the air traffic controller gave was also not left and right, although the impression may have arisen. It said, descend flight level 350 for traffic at your 2 o'clock. So this is the relative direction, is you just use the 12 numbers on the clock, so it's 2 o'clock, when in fact it was on 11 o'clock.
Hi. Now your conclusion from the Überling crash is quite different from, for example, when you say a pilot makes a sometimes stupid mistake. The major difference, I think, is in the Überling crash, there's a real dilemma. I mean, yes. Even without that flaw of the human, like saying the other airplane comes from this direction, but actually it comes from that direction. Yeah. Even without that mistake, both planes are in a real dilemma, or the pilots are in a real dilemma. I mean, one could really obey, so to say, to the human advice. The other could obey to the suggestion from that automatic system.
In this
now,
case,
excuse me, my question is then very simple. How often does it happen that you see a real dilemma like this, as opposed to human flaws?
We really don't know, because unless it really is an accident or an incident that is investigated, we never get to hear about it. So I really can't say. And even if there is, in most cases, no accident happens. So, yeah.
Is it very rare?
No, I don't think so. There are really, I don't know the exact numbers, but there are many cases of TCAS resolution advisories. But I think a case like this, where there are really conflicting instructions between air traffic control and TCAS, are rare, yes. Because normally air traffic control tries to keep at least 4 minutes separation. So in TCAS only gives resolution advisories at 30 seconds. That was the idea with the design of the TCAS system. The premise was that TCAS only works and gives resolution advisories when ATC is asleep and is out of the picture. And that premise, as we have seen, is not generally true.
Okay. Any more questions, please come forward and talk to Bernd directly. We're kind of 5 minutes over our time now, I think. So, thank you, Bernd.
You're welcome.